AWS Lambda Functions are both the darling of frugal cloud architecture and the bane of local development and testing. Do you wish developing and testing Lambda Functions was more local and easy to do? Do you wish you could dev test your initial Lambda code as easily as a unit test run? Do you wish to be free of custom make files that you will not be around to explain to people? And do you wish people would just suck it up and document their work? Well, good luck getting that last wish granted, but let's check out Rust ecosystem's answer to the first three. cargo-lambda is a neat tool released by AWS to make life easy when it comes to developing, testing, and releasing Rust Lambda functions. It's a custom cargo command with subcommands to create, develop, test, build, and deploy Rust binaries to AWS Lambda with minimal effort needed from the developer in all of these steps. Let's start by installing the cargo-lambda command first. There are actually several ways to install this, but the easiest method is to just use pip, the Python package management tool. Now it might be a bit surprising why Rust needs pip, a tool in the Python ecosystem, to install custom cargo commands. It's for the simple reason that it is the easiest approach. This isn't the only place cargo-lambda uses tools from other programming languages or programming language ecosystems to get tasks done efficiently. It also uses the SIG language toolchain to cross-compile the Lambda function code so that the resulting binary is able to run on the customized AWS Lambda infrastructure. Using pip is an easy way to install all of these dependencies and cross-compilation targets without having to set them up manually by yourself. So we run pip3 install cargo-lambda to install the custom command, and it sets up all of these dependencies that we need. After that, it's time to create the Rust Lambda project. Just like cargo new command, we can use cargo-lambda new to create a new project. This time though, we are asked a couple of questions. First, whether the Lambda function is going to be invoked directly through an HTTP call or not. Now, depending on this answer, the template code that is generated changes, because the payload received by a Lambda function that is directly invoked through HTTP is going to be different from the payload that is received by a Lambda function that is triggered by an event in other AWS services. So for this example, let's make a Lambda function that is triggered when an object is created in an S3 bucket. So for that, we need to answer no for the first question and then select S3 event from the list that we get for the second question. Now our project is generated, so we can go and check the file contents. If you take a look at the cargo toml file, you can see that a couple of dependencies have been added for us already. These are for our code to use and also so that our code will be invoked inside the Lambda runtime. A couple of logging and tracing related crates have also been added. Now that provides a really good baseline for your project to start. Let's open the main.rs file. Unlike the usual hello world program you see, we have a more fleshed out starting point to write our Lambda function. This helps us focus on writing the business logic and avoid being bogged down in the details like setting up all the collateral and writing the boilerplate code. Tracing and logging is set up, the Lambda handler function is set up, the payload is deserialized into a proper struct, and we just have to start writing and start utilizing the events. Let's simply output the S3 event that we receive in a pretty format into standard out. Now that our sample logic is done, it's time to start testing our code. For our case, there isn't much to test, but it anyway involves mocking a sample S3 payload. Usually, you would have to do this in a way that doesn't involve actually triggering the Lambda handler part of the code, because your local dev testing will not be working with the AWS API. You'd probably call another function that actually contains main part of the business logic without going to the Lambda handler function. Or maybe you have a more advanced setup where you have local stack to work with for dev testing. In cargo-lambda, you can just start and invoke the function without having to set up mock APIs or having to change the source code to suit your test case. First, you start a hot reload loop for your Lambda function code by running cargo-lambda watch. This is similar to the hot reloads you may have seen in the JavaScript ecosystem. Every time you change a source code, it gets compiled and run. After the Lambda function is started and it's ready to receive events, you invoke it with a sample payload of choice. You'd normally have to build this test payload yourself, but here too, cargo-lambda has your back. When running cargo-lambda invoke command, you can use a sample payload from a library of test fixtures packaged in cargo-lambda itself. You can access this list of sample payloads in this GitHub repository. For an example, for our case, we're going to need to use the sample S3 event payload. So what I do is I'm just going to scroll down and find the proper file and going to use the name of that file without this prefix and the suffix like this. There, we just ran the first successful test run. All without using AWS, without setting up mock APIs or even changing the source code. Again, this is about the developer experience. You only have to worry about writing the business logic. Now that our code is successfully dev tested, we can build and upload it to a Lambda function. Like I mentioned before, AWS Lambda runtime is a specialized Linux environment. So regardless of your development setup, the source code is getting cross-compiled with the Lambda runtime as the target runtime. Also, if you want to target the Lambda Graviton ARM runtime, you can also cross-compile from an x86 architecture as well. So you don't really have to compile within an ARM architecture for you to target a Lambda Graviton runtime. Let's first build our Bootstrap binary. Rust is supported in AWS Lambda through the OS-only runtime, so you have to pack your code to a binary called Bootstrap. With cargo-lambda, you can do this by just running cargo-lambda build. If you specify release flag as part of the build command, the resulting binary will have a couple of optimizations suitable for the Lambda runtime. These optimizations like the binary size, removing unnecessary debug symbols, or even how panics and errors are reported back to the Lambda logging layer. Now that the binary is built, it's time to upload it to the Lambda function. If you haven't already created a Lambda function in AWS along with the associated resources like IAM roles for the function to execute, you can have cargo-lambda create them as well. However, it's not such a great idea. Let's see why. If you just run cargo-lambda deploy without specifying an existing Lambda function, cargo-lambda will try and create the IAM role and the function and then deploy the binary to that function. However, this requires cargo-lambda having access to IAM APIs from your terminal or the pipeline that you run this command from. Security-wise, this is not a great practice because IAM is a critical service in the security of your cloud platform architecture. So it will be better if you can restrict access to IAM from, for example, end-user terminals. Another reason to not use cargo-lambda to create these infrastructure resources is that it's simply not able to manage their lifecycle effectively. It's not an infrastructure as code tool, for example. It doesn't maintain the state very well. It doesn't manage the lifecycle of resources. A better design is to have your infrastructure management layer. That could be infrastructure as code tools like Terraform or CDK or let's say Pulumi. Manage those resources, say create and maintain the lifecycle of the Lambda function and the IAM role, and then have cargo-lambda just build and deploy the binary, say from within a CI/CD pipeline. This way you can minimize access to AWS IAM and also manage your infrastructure with tools that are better suited to do that. For our scenario, let's just skip all of that and create and deploy the function because I want to keep this short. I'm just going to establish an AWS session with temporary credentials. These have the proper permissions to perform the IAM API calls that we were worried about. Also, they have multi-factor authentication associated with the temporary credentials. So the usual limitations of the temporary credentials that you get from AWS STS API do not really apply here. And I can just run the command without having to worry about access or other permission issues that cargo-lambda will probably come across. After running the deploy command, I get the ARN of the function created. Let's go and check it on the AWS Web Console. We can see the function has been deployed. Let's add a trigger to it from an S3 bucket so that the function gets triggered every time a file or a new version of a file is uploaded to a specific S3 bucket. I'm just going to go and configure this S3 bucket. I'm going to add an event notification and specify the Lambda function as the target for this event. And I'm uploading a test file into the S3 bucket. And that triggers the function as expected. We can go into the CloudWatch logs and see the output of the function. We just pre-printed the S3 event we received in the Lambda function. So this JSON output is what you would see. So that was the start to finish development lifecycle of a Rust Lambda function with cargo-lambda. Its emphasis on improving the developer experience is a refreshing approach for cloud development, and also it's impressive how AWS has been able to do this and keep things simple. For now, that's me. If you find this video helpful, please take some time to like, comment, and subscribe if you haven't already. Thank you so much for watching. See you next week.